So let's look at the electrostatic field. We've looked at Coulomb's law, and we want to now look at what's called the electrostatic field. Well, imagine that you have a region of space that's surrounded by a distribution of charge. These could be point charges, so we'll call those Q sub I, or a continuous blob of charge, or you could have both. So let's suppose we've determined the total force, and we'll call it FQ test on a test charge, this Q test, located at position R relative to some origin. This is the charge distribution. Here's some Q sub I's. Here's a blob of charge. We've got an origin at O, and we have a test charge at the position vector R, and let's just suppose this is the resulting force on this test charge due to the presence of all these charges. Well, we define the field at this point here, same point, R, as the limit of 1 over the test charge times the force, the electrostatic force, on Q test charge at R. So one more time, we divide the force by the Q test, take the limit as Q test goes to 0. That's the definition of the E field at this point. For a single charge, if you just had a Q sub I at R prime sub I, the force on the test charge would just be the Coulomb's law, and so we would obtain the E field by dividing by this Q test, which by the way just eliminates the need to take the limit, because what we have for the force is K Q sub I, and we'll worry about the R factors here, times Q test. So to find the E field, we divide by Q test, and so you can see that it doesn't exist here, so there's no need to take the limit. So what are all these R factors? Well, this is Coulomb's law, and what R minus R prime represents, if you recall, is the vector from the ith charge, or the charge Q sub I, to the Q that's sitting at the position R, which in our case is Q test. So that's the vector R minus RI prime. Well, if you take the difference between R and R prime sub I, then you'll get this vector, and that's what we call funny R. And in this case here, if you let me write it like this, this would be funny R I, because it's from the ith charge to the test charge. Okay, one more time, we divide by the test charge magnitude, and so we end up with the E field due to a single charge given by this expression here. Well, we can write this in several ways if we want to introduce the funny R. So here's the funny R, the unit vector, and if you come back down here, the funny R unit vector is equal to the vector funny R divided by the magnitude of funny R. And so in terms of the difference vectors, it would be this quantity here. If this is the distance squared, that's the length of this vector right here. So you have K over Q R squared, which is the normal quantitative part of the Coulomb's law. This unit vector just simply tells you what the direction of the E field would be here. So notice that it has the Q sub I here. If that's positive, then the unit vector is going to point in this direction. So if you think of this E field, then at this point right here would have the direction like this. So this is the direction of the E field at this point. To nail this, E is a vector defined at a point, and the point is defined by the position vector from the origin. So that's how we talk about E fields, and so if you let R wander around through space, you'll get the E field at various positions relative to the origin. Here's our vector, funny R, which is defined like this. Here's our unit vector, and it's not uncommon to replace the QI to Q just to give you the correct orientation of this unit vector with R sub I, but then you have to remember that it is pointing from QI to Q. If QI switches sign, if it's a negative sign, then R sub I will point in this direction, because this vector here, the E field, will switch direction if we switch sign, and that's because of the sign change right here. So to say it correctly, if we have positive charge, we point away from the Q sub I, so we are in the direction of the unit vector funny R. If we change sign, we're in the opposite direction to the funny R, and so in this case here it would reverse and go in this direction. Well, if we have a bunch of charges, so let's start worrying about these over here. Let's say we have capital N of them. Then just as we added up the force due to several charges, we can also get the E field. And so what we do is we just simply sum over I, this is little I, from 1 to n. You're assuming superposition, which is reasonable. So here's the E field due to n of these q sub i's, located at r sub I, and I put a prime on that. These are evaluated, the E field is evaluated at the field point, which is the vector r. So if you go back to our single charge, where we just had one q sub I, what we do now is just add them all up. So we add up from I equals 1 to n, because n is the max number. What we have here is exactly what we had for a single charge q sub I. We can write it in different ways because this is our vector funny r. If we take this and divide by r minus r prime I magnitude, we'll get this. And so if you look here, if we have the vector funny r, then we'll have this quantity cubed. If we have the unit vector, then this becomes square. So just don't forget, all these combinations of r minus r prime will give us these various funny r vectors. If we just keep track of that, we can use either the funny r's or the vectors themselves. We've got a blob of charge up here that we haven't talked about, so we're going to consider how to handle that in just a little bit. So let's take this simple example. We have 2 point charges separated by a distance d. We have a point that's on a symmetry axis, the z-axis, and so you can see that there's some symmetry here in the sense that these are equidistant from this axis and they're oriented along the x-axis. Let's take a look at this. The way we're going to solve it, first of course we're just going to add the fields due to these 2 charges, so that's the superposition assumption. And if we look at the E field from each q, it has both x and z components. So for example, the field due to this charge at this point here would be off in that direction like that, and this one would be off in this direction. Sorry for the crude writing here. So they have both x and z components. The z components are in the same direction, and they're equal in magnitude because of the symmetry. So in other words, this component here is in the same direction, so those are going to add. On the other hand, the x components are in the opposite directions. If we consider the fact that they both have the same magnitudes, when we add them, they're going to cancel. So they cancel. So the total E in magnitude is equal to 2 times E sub z magnitude from one of the q's. And so we'll take advantage of the fact that we don't have to calculate E sub x, and if we know E sub z from one of the q's, we just multiply by 2 to get the total. So here's another picture of this, and so we put in the vector that goes from q to the point, and then we simulate the E fields due to those 2 point charges. So this is E2 due to this charge here, and this is E1 due to this charge over here. Again, because of the symmetry, we have 2 equal angles. If we're going to find the E field, we're going to have to worry about this distance here. Here's another picture of the same thing. We're going to call this leg of the triangle right here, we'll call that L. So the first thing we do is we write down the z component of the E field. This is for one of the q's. It will just be kq over L squared. That's Coulomb's law. But then we change that to the z component by multiplying by the cosine theta. So if you have theta very large, then this will go to 0, and so you'd have no z component. If you have the theta very small, then you'd be adding vectors that are close to the z-axis, and that would give you a large number. So this approaches 1, and so if we write now the cosine theta in terms of this triangle here, the cosine theta is the side adjacent divided by the hypotenuse, and that's right here, z over little l. Combining those 2 factors, we have kqz over L cubed. Well, what's L? L is a right triangle, so we just take z squared plus d over 2 squared, and that will give us the length of the hypotenuse. So that's right here, we take the square root. So now we can come back over here and write down E sub z for one charge, and it will just be kqz over L cubed. To get the total E field, we just multiply by 2, and we remember that it's in the z direction only, and so we end up then with this expression for E total. Looking at this, you can see that because this is 3/2 power here, as z gets very large, you'll still have a z in this position here. It'll be something like z cubed, and so therefore the z divided by z cubed will give you something that will look like 1 over z squared. So it's going to drop as you increase z. But let's take a look at a plot of that function. So we're only looking at the magnitude of this. So this is the magnitude of E total, which is E sub z. And here's a little plotting routine from Mathematica, and this is the result. And you might be surprised that it in fact goes to 0 at the origin. Okay, so as you leave the origin, you come up and you actually get a maximum value of the magnitude of the E field. Then as you go further, it goes into this decay, which remember I said when z is large relative to d over 2, then you'll be 1 over a number which will be increasing, so therefore this decreases. What is the reason why this goes to 0? Realize that if you're sitting right here, you're between 2 point charges of equal value. If this is positive, it'll be pushing this test charge this way. If this is positive, it'll be going this way. They're the same sign, so therefore it cancels. Switch the signs of Q, and all it does is switch the directions. That's why you have 0 here. Well, if you're 0 here and you're non-zero up here, then obviously you've got to increase. Okay, so what we do is we let z be really large relative total spacing is d, of course. So we're in a situation like this, so we're considering z much larger than d, and let's see what happens. So we start with the expression that we just derived. This is the exact E sub z from the point charges. And we take this denominator and treat it as a number where this is large compared to this, and we factor it so that we can bring out a z squared times 1 plus, and then you can see what I've done. I've just put this z squared back, so z squared times 1 over z squared was 1, which brings us back to this thing. Bring the z outside, and what you have, because of this 3/2 power, you get z cubed on the outside, and then you have 1 plus this quantity to the 3/2 power. Well, take a look at this. So now we have z times this, that's the original expression, and we rewrite it in terms of this quantity here. So z divided by z cubed will give us 1 over z squared, and here's our factor right here, and that'll be minus 3/2 because we bring this upstairs and put the minus sign here. So all we've done is written this as minus 3/2. Where the factor that we're talking about bringing up is the 1 plus this quantity here. If you take an expression like this and expand it in a Taylor series, then what you get is 1 minus 3x squared over 2 plus higher order terms. The first term would be order x to the 4th. But look at what x is. It's this quantity here. So as z gets larger compared to d, then x is going to get smaller and smaller, and of course it's much less than 1 for very large d. So if we look at this, then we just write this for z much larger than d. So here's our prefactor here, times 1 minus this quantity here. I've included this just simply to show you what this looks like in terms of the first term. Now we buy totally into the inequality. And so this term here is going to drop out if we go far enough away. D squared over z squared allow us to just throw it away. We drop it, and so we end up then with the total E field at very large distances approximately equal to k times 2q over z squared. Well, that's equivalent to a point charge 2q at the origin. So as we go farther and farther away, that's what I meant. It looks like these things are approaching a point charge. And so we end up with just a point charge E field at very large E. And realize, of course, that such a E field would only be in the z direction because of the fact that the charge is sitting at the origin.